So having discussed the characteristics of a good blob detector, that one is that it should be able to operate at different scales in an image, and the response of the detector should be largest in magnitude when the location and the scale of the detector matches with that of the blob in an image. So a natural question is, what kind of a detector or what kind of a filter would be appropriate for such a task? That is, it should be able to operate at different scales and the response should be highest when the location and the scale match. Given that we are no longer searching for isolated points in image. Now we are looking for regions or a cluster or a group of pixels in an image that share some common property, and often that property is going to be associated with the color or the grayscale values of the pixels in an image. So the question is, what kind of a filter will achieve this? Recall that our goal is to detect regions and not isolated points with these two properties. So the filters that can achieve these objectives are known as center surround filters. Where a center surround filter usually has a region of negative weights So we have negative weights over here, and it is surrounded with region, a small region with positive weights outside. So this blue circle shows, so the region between the blue and the white circle or ellipse is a region of positive weights. And definitely we can have a negation of this, where the center region has positive weights and the surrounding region has negative weights. We can draw that in the same color for we are drawing it with the same color so that we can relate these two examples. So in this case, the region between the pink and the white circles or ellipse is region of negative weights, and the central region has positive weights. And definitely there is going to be some dimension of this filter. So the size of the filter is W. Again, W cross W filter. So the remaining portion has zero weights. So in this example, we have considered filters that have ellipsoidal or circular shape, but we can generalize it to any other shape as well. For example, we could have a squared or rectangular filter as well, where the central region detects rectangular or squared blobs in an image. but for the task of generalized blob detections in an image, the filter that is going to generalize well for arbitrary shapes of blobs in an image is going to be either circular or ellipsoidal in shape. So circular and ellipsoidal filters can generalize well for arbitrary convex or non-convex shapes, but the other shapes of filters like squared shaped center surround filters may not generalize well for different kinds of blobs in an image. Furthermore, the inherent mathematical function that generates such filters is going to have a simpler formulation for ellipsoidal or circular filters, and it is going to be complicated for rectangular or squared filtered shapes. And therefore, going forward, we would be discussing filters that are ellipsoidal or circular in shape. And here, both of these filters will work for blob detection. The only difference being is that the response of one filter is going to be positive for some blob and the response of other is going to be negative. But since we are concerned with only the magnitude, the sign, the positive or negative won't make any difference. This filter will give large positive response when the central pixels are dark, surrounded by light pixels. Whereas this one will give a negative response for such kind of blobs. Similarly, this filter will give positive response for a group of pixels that are light in color, surrounded by darker pixels. Whereas the response of this filter is going to be negative and the response for this filter is positive. Similarly, when the central is dark and the outer is light, we have positive response from this filter and we have negative response from this filter. And thus the sign of the response is not going to make any difference. So now that we have discussed that the center surround filters can detect a group of pixels in an image that share some common property, and often that property is concerned with the grayscale values of the pixels, the other important characteristic that we discussed was that a filter is a good blob detector if it can operate at varying scales, and also when the response is largest when the scale and the location of the detector matches with that of the blob. So let's consider an example. Let's assume we have a perfect circular group of pixels over here with radius R1, and we have a scaled version of the same group of pixels with radius R2. And let's assume that all the pixels over here are darker and all the pixels surrounding this pixel are light. And same is the case over here. We have a dark group of pixels and surrounded by light intensity pixels. So we can see that that the center surround pixel, for example, if the scale of this filter matches exactly with the scale of the blob, let's consider that our filter is a circular center surround filter. It means we have some radius R3, all these weights over here are negative, surrounded by a region of positive weights. And all the other weights are 0. We can just leave the 0 weights by black color, so we don't have to draw them in green. So now let's assume that R3 is equal to R1. So in this case, we see if we match the center of the detector with the center of this blob, then we are going to get a very nice response, a very high response. So if we place this blob detector over here, where this distance is less than R3, so assume that the center of the detector is same as the center of the blob in an image. So in this case, you can see that we will get, so all these weights are dark over here, and we have a dark group of pixels over here. And for simplicity, assume that the dark pixels are totally black, that is the value of all the pixels inside the circle is 0. So in this case, and the outer pixels are all 255. In this case, we will have negative weights multiplied by 0, so we'll have 0 plus the positive weights multiplied by 255. So we'll have some positive number lambda. And we see that we have a response of lambda when the scale perfectly matches with the scale of the blob. Now let's take the same filter with radius R3 and place it on top of the blob with radius R2. And so this is an image. So when we place the filter over here, and let's assume that the outer circle has some radius R4, where R4 is less than R2. So in this case, we can see that the negative weights are going to be multiplied by 0, and the positive weights will also be multiplied by 0. So we have a total net response of 0. So similarly, we can keep on increasing R3 and R4. So if we keep on increasing R3 and R4, and at some point R3 will be equal to R2. So if we keep on increasing R3 and if it becomes R2, then we can see that the response now is going to be some value lambda 1. Since we'll also have to increase the size of the filter, and the difference between R3 and R4 may increase, and the number of weights that are positive may increase, and we do not know the exact value of the response, but it is going to be some value lambda 1 for a filter that is sufficiently larger compared to the original filter with radius R3 and outer radius R4. So we can see that this center surround filter, we can increase the size of the filter arbitrarily depending on the size of the blobs that we have to detect in an image. So we can see that the center surround filters satisfy a very important property, that they can operate at different scales in a same image. And also we can see that the response is going to be highest when the location and the scale of the detector matches with that of the blob. And thus center surround filters are used for blob detection. So now assume that we have a general image I that contains both these blobs, one with radius R1 and one with radius R2. So we can have multiple copies of our blob detectors. For example, we can have a small filter where the size W is equal to W1, and the radius being R1 in and R1 out. And similarly, we can have a large filter with W going to be W2, where W2 is larger than W1, with inner radius R2 in and outer radius being R2 out. So this filter can be used to detect small blobs in an image, and this filter can be used to detect blobs that are large or significantly large in an image. And similarly, we can have blob detectors at intermediate scales. So we see that the center surround filters actually can operate at varying scales in an image. And furthermore, we also see that the response is going to be maximum when the scale and the location of the detector matches with that of the blob in an image. For example, let's assume that R3 over here is equal to R1. So when the location matches exactly, we are going to have a response of lambda. But if we shift the detector by some small distance, but still inside this region, let's suppose we have location x1. If we place the filter at location x1, now we see that some of the high intensity pixels are going to be multiplied by negative weights. So we'll have some small value negative gamma, plus we have both the zero valued pixels and large valued pixels being multiplied by the positive weight region. And we convolve, and obviously here the operation that we are performing is a convolution operation. So we'll add all those individual multiplication of the weights and the pixel values, and we are going to get a new value lambda 2, where definitely now lambda 2 is less than lambda, because some of the positive weights are now multiplied by value 0, as opposed to earlier case where all the positive weights were multiplied by large values and we got the response lambda. So now we can see that we not only have response lambda 2, which is smaller than lambda, we also have a negative response of the negative weights, and now the value is going to be significantly less than lambda. So the original value here is, let's say, lambda 3 with a summation of lambda 2 and negative gamma. So we see that the response lambda is higher than lambda 3. And at some point when the detector is totally far away from the center, if you place the detector over here, then we see that the response is going to be 0. Assuming that the summation of all the weights inside this filter is 0. So if we sum all the weights, that summation is 0. So in this location, in this region, we're going to get a 0 response. So perhaps we can plot the response of the blob detector with varying locations when we go away from the center of the blob. So at the center, we are going to have the highest value, and the response will fall from thereafter, and it will become 0. Similarly, if we go towards the left side, we'll have such a response. So we see that that the center surround filters, number 1, so 1, they can detect blobs, they can detect a region of pixels in an image. So the center surround filters can detect a group of pixels sharing same property. Number 2 is that we have seen that they can operate at multiple scales in a same image. Furthermore, as we saw, that they produce a response that is highest when the location, so the response is largest or highest when the location and the scale matches with that of the blob. So this discussion establishes the fact that center surround filters are good for blob detection, and they also have the two key important characteristics of a good blob detector. And in this course, we will discuss two such center surround filters. But before that, we will revisit the topic of scale and the importance of being able to operate at different scales in an image for blob detectors.